Hi there, welcome to your lesson on the first derivative test. Let's begin by talking about maximum and minimum points and intervals of increase and decrease. So let's take a look here. We have two parabolas, one concave up, one concave down. When we have a concave up parabola, the vertex is and let's say the vertex here is 3, 2. We say the vertex is a local minimum point. We've also always called it a minimum point, but now we're going to call it a local minimum point. That means in this region of the graph, we can say this is the lowest point. In this case, this is also called the global or absolute minimum because no matter how far you go along the graph, this will be the absolute minimum point. Likewise, on this concave down parabola, that point, we can say the vertex is 2, 4. Is called a local maximum because in this local area it's a maximum point, but also globally or absolutely, that means along the entire function, it is also the maximum point. Let's compare that to somewhere where we have points that can be local max or min but are not global. So look at this one here. Okay, on this graph, we assume when we don't see arrows on a graph that there are arrows and that it continues forever. So here it continues forever, here it continues forever. So here's that point at negative 0.9 and 8. And here we can call that a local maximum point because in this local region is definitely a maximum point. However, it is not a global or absolute maximum because if you follow the graph to its end over here, this arrow meaning it goes up forever, it means this point is not the maximum because along this curve here there's points that are higher than that one. So this is only the local maximum and not a maximum for the entire function. Likewise over here, 2, 1, negative 4. 2.1, negative 4, we have that point. It's a local minimum, but it's not a global or absolute minimum because it's only a local minimum. It's only a minimum in this local region, but if you follow the curve to the end here, we go lower, 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 lower. So this is only a local minimum, not a maximum. Sorry, not a absolute minimum. All right, so looking at that, we can also say where the graph is increasing and decreasing. So the graph from negative infinity to negative 0.9, because this is negative 0.9 here, it is increasing. So increasing, and notice, remember these symbols mean not including these values. So we cannot include negative infinity, and we do not include negative 0.9, because at that point, the graph is neither increasing nor decreasing. It is just nothing. It's just a point where it actually changes from increasing to decreasing. So here it's increasing. And from this minimum point, the graph is also increasing. So it's also increasing from 2.1 x value towards infinity x value, right? We're giving like a domain where it's increasing. Again, not including 2.1 or infinity. Likewise, in between this period of increase and this period of increase, we have the graph going down. So in between here it's decreasing. So we can say the graph is decreasing from negative 0.9, so negative 0.9 x value, all the way to 2.1, this x value. So between those values it's decreasing. And again, we don't include them because at those values it is neither increasing nor decreasing. It's changing from increasing to decreasing. Okay, pause there and just take a look at that. This is the important vocabulary for what we're going to look at today. Okie dokie. On this one here, again, we see a graph. Here's a absolute minimum because it's the lowest point on the whole graph. It's also a local minimum. This one, what's this one? Okay, that's a local maximum, but not an absolute maximum. How about this one? Local minimum, but not the absolute minimum. Okay, great. So now let's move on to make our way towards the first derivative test. We have a graph of this function right here. And let's find the derivative of it and then fill the table below. So once we find the derivative, let's find what does the derivative equal when x is negative 2, negative 1, and so on. So first of all, the derivative is this. Okay, check your work. Now put in negative 2 into the derivative function and see what you get. Okay, 36. Now put negative 1 in there. 15. Now fill in the rest of this table. Okay, when you put 0 in there, you get 0. When you put 1 in the derivative, you get negative 9. Then negative 9 again, 0, and 15. Now take a look at that. Look at the graph. Think about what we talked about, increasing and decreasing intervals. And do you notice a connection between derivative values and when the graph is increasing and decreasing? Okay, I hope the connection is clear. We see a positive derivative here, and that's occurring over here when x is -2, -1. So down over here, the graph is increasing. And at those times, the derivative is positive. That makes sense because the derivative tells us the slope. And here the slope is positive when it's increasing. Then we get to this point here. At x equals 0, we get to this peak. And there, the derivative we know, let me just put that on here. We know the derivative is the representation of a tangent line, which is horizontal there. There is no slope at that peak. And we can see no slope represented here by a slope, a derivative value of 0. And then the derivative is negative because that makes sense. We have a negative slope. The graph is now going down. It's decreasing. So we see a negative slope, negative derivative value. Then at x equals 4, the derivative is 0 again. So here is x equals 4 right here. So it's the bottom, the minimum point right here. And there we know again, okay, let's see. Yeah, here x was 0 and the derivative was 0. Here, x is 4 and the derivative is also 0 because there's no slope at that point. And we can see here no slope at that point. And after that, when x equals 5, it's increasing again, derivative is positive. So the derivative tells us all about how a graph is increasing or has no slope, which means a peak, or a bottom point, and then decreasing, increasing. So here we can see this graph is increasing when x is less than 0, and we can see that here, the derivative values are positive. And at union, that means also it is increasing when x is greater than 4. So here's x is 4. When x is greater than 4, it's increasing. We can see positive derivative. And it's decreasing here between 0 and 4 because we see a negative derivative between 0 and 4. Negative slope means it's decreasing. So again, pause here and take a close look at everything. We're starting to put all the pieces together between derivatives and what they tell us about when graphs are increasing or decreasing. All right, so we've kind of concluded now. When the blue lines here, so we have a red curve, and then we have the blue lines representing the tangents. We can see the tangents show a negative slope when the graph is decreasing. Then at the vertex here, there will be no slope, and then the tangents are positive. So the function is decreasing when the derivative is negative, and the function is increasing when the derivative is positive. That makes sense. All right. And this, by the way, is called a stationary point when there is no increase or decrease. It's just that point between increase and decrease. All right. So here's a summary of that. We see this function here. And written in some mathematical notation we have, if the derivative is greater than 0, so that means a positive derivative, for all x values in a certain range of values, like from a to b, then f must be, the function must be increasing between those values, right? If the derivative is always positive for all those values, then the function must be increasing there. So the opposite of that is if the derivative is less than 0, that means negative. When we see a negative derivative for all x values in a certain domain, then the function must be decreasing between those 2 points. All right, so for example, here, every derivative value from here to here would be a positive value. And that tells us the function must be increasing from here to here. And from here to here, all the derivative values would be negative. So that means from here to here, the function is decreasing. And again, from here, the derivative would always produce a positive slope. So from here to here, the function's increasing. That's all that terminology there means. Increasing. Derivative is 0 here, decreasing, less than 0, and then increasing, and the derivative is greater than 0 again. All right, there's these weird points like this that happen, and we can say that the derivative is actually undefined there. We won't deal with those too much though. All right, so let's try a couple problems. We have this one to start off. Look at this function, and let's find the derivative to begin. Okay, here's our derivative. Now, without the graph, we want to figure out when the graph is increasing or decreasing. And we know it will increase or decrease when the derivative is positive or negative. But we know that in between these periods of increase and decrease, it has no slope. So when does it have no slope? Well, it has no slope when the slope is 0, right? So you set the slope equals 0 and solve this. Let's see what values we get for x and talk about what those values represent. So solving that, can factor out the 3. We can factor that difference of squares into these two factors. And that means our two values for x are these. So what do these two values represent? Okay, these two values represent the points on the graph where the slope is 0. And when the slope is 0, it means we're either at a max or a min point. That means beside each of these points, the graph is either increasing to get to it or decreasing, right? So we know we're at a max or min. So now we just got to find out what's happening on either side because we don't know if it is a max or min. Is it a max? Is it a min? Well, we got to find out what's happening on either side. So what we're going to do is begin with that we know that the derivative is 0, therefore there's no slope at these 2 points. So we're going to check what's happening to the left and to the right of each of these 2 points. For example, we're going to take -2 because -2 is to the left of -1. So we take an x value of -2, we put it into the derivative. So figure out what you get. What happens when we put -2 in here? And don't worry about the actual value. Just tell me if it's positive or negative. Okay, it's positive. When -2 goes in here, we get a positive answer. That means that when we are at x equals -2, the slope is positive. And we already know at x equals -1, we have no slope. So if it's positive beside it, it means it's rising, the graph is increasing and coming to this maximum point that must be here. Now let's try what happens when you put 0. And why 0? Because now I'm looking between -1 and 1. Because again, I know at -1 and 1, there's no slope. So what's happening between those 2 points? So a 0 is a point between -1 and -1 and 1. So put that in there, and what do you get? Positive or negative? That produces a negative value. So that means between -1 and 1, the graph is decreasing. It has a negative slope. It's decreasing. Okay, now let's try beyond 1. What happens after x equals 1? So let's take any point after x equals 1. For example, 2. And you can take any value here. You could use 3, 4, as long as it's after x equals 1. So what happens when you put that in there? Positive or negative? Positive. All right, so after x equals 1, the graph is increasing again. So we've been doing this without seeing the graph, but I'm going to show the graph in a minute, and it's going to help us really see how this all works together. But it's important that you can do this and understand conceptually what you're getting from it. So let's take a look at that. So we know the graph must be increasing from -infinity to -1, because from -infinity we see positive slope. You know, before -1, it's a positive slope. So it's increasing. It reaches -1 where the slope is 0. So it's increasing only to there. And then also, it is increasing from 1 to infinity. Why? Because after x equals 1, see we have a value of 2 here, we see positive slope again. So it must be increasing again. That means it's decreasing between those 2 points because we see a negative slope between -1 and 1. It's decreasing between -1 and 1. So again, let's get the graph here because the graph will make things a lot clearer, hopefully. Here's the graph of this original function. Here is the point -1, 6, so x value of -1. When we solved this, remember, we found the derivative and we found when the derivative equals 0 by setting equals 0. So we were saying when does the graph have no slope? And that makes sense. Over here we have no slope. We have a horizontal tangent line. And over here we have no slope. So when x equals -1, no slope. When x equals 1, no slope. And that's what we found here. And when we're doing this part here, we're figuring out what's happening before and after each of these points. So if we have x equals -1, we checked what's going on with the graph before -1. And we put a value of -2 into the derivative. So we went to the left of -1, we put a value of -2 into the graph, and we found out it produces a positive value. That means the slope of the graph is positive, and we can see that here. It's increasing. Okay, then we said, what about, let's look at an x value between -1 and 1. So we took an x value of 0. So between -1 and 1, we have an x value of 0, somewhere in here, and I put that value into the derivative, and it gave me a negative value. That means the slope when x equals 0 is negative, and we can see here the slope is negative. The graph is decreasing. Finally, we took a value greater than 1, value of x equals 2, put it into the derivative again, and we got a positive value. That tells us after 1, when x values are greater than 1, it's increasing. And that's what we've labeled here. So pause here and take a look at it closely. There's going to be a second video that continues, and you're going to try some more problems. Let's keep going.